So let's discuss the Kirchhoff's law. Okay. So before talking about the law itself, we have to discuss two definitions of two quantities. Okay. So first is the absorptive power. Absorptive power. Okay. So what is absorptive power? Say we have a body given to us. Say this is the body, and there are these are waves, energy waves. Okay, they may be in the form of light, in the form of heat. Okay, so basically these are energy which is incident upon the box. Incident upon the box. Now let the total amount of energy incident on the box be capital ET. Okay, and the box will absorb only a certain amount of the energy due to the properties of the material of the box. Okay, and so let the energy absorbed by the box be EA. Okay, different materials can absorb different amounts of energy. Okay, so for example, for black bodies, which are ideal bodies, they absorb all the energy falling on them. Okay, they can absorb energy from all spectrum. That is, the frequency of the energy absorbed by black body ranges from all spectrum. It goes for all spectrum. Okay, but in our general body, in reality, the bodies that we see or the bodies that exist cannot actually absorb all the amount of energy falling on them. They can only absorb energy between ranging for a particular spectrum. Okay, say so let this be EA. And what is absorptive power, if you ask? Let me clear the space. Okay, so what is absorptive power? Absorptive power is the amount of energy absorbed, which is EA. Okay, it is this ratio, the amount of energy absorbed to the total amount of energy falling on the body. Right, so this is the absorptive power of a body. Okay, it's simply the ratio. Now, as all the radiation incident on a black body is absorbed, right, so the absorptive power of a black body is unity or 1. So for black body, A is equal to 1, as EA is equal to ET. This is for black body, right? Okay, now let's come to emissive power. So let me clear this screen. Okay, let's now talk about emissive power. Now let's talk about emissive power. So I'll make a body now. Okay, we will consider an area of the body. Let us consider this portion of the body. Let the area of this portion be delta A. Yeah, it's a very small area. Okay, delta A. And we'll consider that. Now we know, you see, this is the interesting part, because the heat, okay, emitted by the body through this area would go somewhat like this, right? It would go somewhat like this. The heat will not move out like this, right? This would not be the end points or something for the movement of heat, right? It will not go just like this, but it will spread out, right? This is what we observe, right? Heat spreads out like this. The heat does not flow in a unidirection, right, like this, but in omnidirection, right, like this. So if we see from this side, right, let me clear out this mess first. Now if we see from this side, okay, we're looking from here, what we'll see this. I'll draw this body again, but this time we're looking from here, okay? We're looking from here, and I will draw the area again of the body. This is the area, right? So we'll find that energy would come out like this, right? We'll get a circle, right? And the edges of the circle would be touching the area that we have considered, right? So this is a solid angle, so we have to consider a solid angle. A solid angle would be formed. I hope I'm able to explain it properly and you're able to visualize, because in two-dimensional surface it's quite difficult to draw a solid angle. Actually it is not possible, because solid angle is obviously 3D and we cannot draw 3D objects in 2D. We can just have a feel for it. So I hope you got a feel. Okay, if you want a video on solid angles, I'll make a short video on that too. Okay, so let this be the solid angle delta omega. Now let me clear out the space and then we'll proceed further real quick. Okay, so this is the solid angle, and now let the amount of heat, okay, amount of, not just heat, it can be any form of energy, so we'll just say energy. Let the amount of energy emitted by this area through this solid angle in time delta t be delta u. Then the emissive power is equal to the amount of energy released per unit area multiplied with per unit time, or I can say amount of energy released per unit area per unit time per unit solid angle. So this is the emissive power of the body. Let me draw a box over here. So this is the emissive power of a body. Now we can finally go through Kirchhoff's law. Now let's finally move on to Kirchhoff's law. So what is Kirchhoff's law? The Kirchhoff's law states that the ratio of emissive power, which we discussed, right? Emissive power to the absorptive power is constant for all bodies, is a constant for all bodies. This is constant for all bodies at a given temperature. Now, for example, at room temperature, 27 degrees Celsius, we are having a pencil box over here. Pencil box. We're having books. We're having a computer, right? So, at room temperature, right, this ratio is constant. That is the amount of energy absorbed by the pencil box to the ratio. I'm talking about the ratio of the amount of energy absorbed by the pencil box to that released by it is equal to the ratio of the amount absorbed by the box to the amount released by it. And similarly, similar cases for the computer as well, and even us at 27 degrees Celsius, even we are having the same ratio as the pencil box, books, and computer, right? And so at a particular temperature, this is the case, right? But however, this is not complete. The law further states that this constant over here is actually equal to the emissive power of a black body at that particular temperature, right? So as I told you, for the pencil box, for the books, for us, for the computer at 27 degrees Celsius, this ratio is a constant, and the law further states that this constant is equal to the emissive power of a black body, right? So if I now just clear the space, and if I change the color and write down the law, it would be somewhat like this: the emissive power of the body to this is the ratio of the emissive power of the body to the absorptive power of the body is equal to the emissive power of the black body at room temperature. So this is for the black body, and this is for the body which is under consideration. So basically this is the Kirchhoff's law. So now what is the final takeaway from this law? The final takeaway from this law is that at a particular temperature, since this ratio is a constant, right, which is equal to this, which is a constant, and so we can conclude that at any given temperature, provided the temperature is constant, since this ratio would be constant, therefore if we increase the absorptive power of a body, then the emissive power would increase, right? And if we decrease the absorptive power of a body, the emissive power would decrease, because E is equal to AEB. This is for black body. So since this is a constant, we can say E is directly proportional to A, right? Another way to think about this is, since E by A is constant, let that be equal to 10. Okay, just for explanation, I'm considering this value. Now say at that particular temperature, the value of E is 100 or 1000, let it be 1000. So the value of A would be obviously 100, right? Since this is equal to 10. Now if I decrease the value of E, let me clear out this space. If I decrease the value of E, say to 10, I will have to decrease the value of A as well to make the ratio equal to 10, because this has to be equal to 10, right, at a particular temperature. The ratio is not changing, but the individual cases might change if we do certain manipulations. Okay, so I hope this is clear to you. Thank you. Consider subscribing to the channel for more videos.